I do have worksheets up for chapters 9, 10, 11, and 12, and the solutions are in the tutorial videos on YouTube. I try to adjust the position of the tutorials so they're in chronological order. So there's, they're near the top because we're in first semester, and those tutorials cover first and second semester. So you should be able to find those to look at the solutions. You'll find a place where I have an awkward pause because I had apparently done my calculation, forgot to put in G when I put in my numbers the first time, and I was trying to figure out how could I have messed up this one? This is one of the easiest calculations we're doing. So I thought about, go back and take out 20 seconds of silence, but yeah, just know what's going on there. All right, so our test, mañana, is on chapters 9 to 12. Don't forget your scrapbook over chapters 9 to 12 tonight. I really apologize for this timing. My wife is having a medical procedure this afternoon, and so I will be with her this afternoon. So I won't be available to help you with questions this afternoon. You can still email me. I'll probably be really bored in the hospital, so I can respond to emails. Okay, reminders for the last 3 problems. I don't want to take off points. You all recognize this, right? I want you to earn as much as you can. So make sure that you include a figure unless you're specifically instructed. You don't need a figure for this one. Include concept. Now this year I've been cutting down what I'm actually looking for in concepts. I'm looking for you to basically identify this is this kind of problem. And so I just connect these ideas. But make sure you have it there so I know what your aim is. And as I've been trying to emphasize ever since we did lab, where I did the problems in lab, if you can identify what type of problem it is, then you basically have, okay, for this type of problem, I'm going to do this and then this and then this. And that should lead me to the answer, even if, I didn't know what to do at the outset. I just identified the type of problem. And so, like when I'm doing the worksheet, answers, I'm trying to make sure I am being explicit about how you know which type of problem it is. Need to show your physics understanding by working from standard equations to find solutions for specific questions. If you take a special case equation, that is, if you take an equation that only works for this problem, you're not going to get credit for it, right? You need to show that you knew how to get there. Otherwise, it's just a math problem, and you guys are all good at math, pretty much. Okay, getting into the actual material that's on the test. Chapter 9 was equilibrium. So how do you know if a problem is an equilibrium problem? The things that make it equilibrium as far as me for identifying, this is an equilibrium problem, are if the motion is not changing. 95% or more of the time, that non-changing motion is stationary. But it could be moving at a constant velocity or rotating at a constant angular velocity. So if there's no change in the motion, then it's an equilibrium problem. If there's change in the motion, it's a dynamics problem. So that's first an easy thing. And of course, even with fluids, we have fluid equilibrium, our static fluids. Those were fluids that were stationary. But even our dynamic fluids, in most cases, we have the fluid is in a steady state that's in equilibrium. So identifying equilibrium, not changing velocity, not changing angular velocity. And then the outcome of that is what everyone was saying. So that's a good connection. If it's in equilibrium, we have 2 conditions. Some of the forces is 0, and some of the torques are 0. Now, in solving an equilibrium problem, which one do I usually use first? Some of the torques is 0. Who has ever whispered that very quietly? No, it was not. Sum of the torques equals 0 is usually the one I start with because I'm trying to solve for something and I can eliminate one of my forces from my calculations if I use sum of the torques and I sum about an appropriate location. Remember, if it's an equilibrium, it doesn't matter where you sum the torques, it's going to be 0. And so if you choose the right place, you eliminate this force. If you only had 2 unknown forces and you eliminate one, you only need that one equation to find the other force. So that's why I usually start by summing the torques about a place that makes sense to me because it's going to eliminate a force I don't know. Yeah, I actually thought the first one was know the conditions of equilibrium here, so that's what I've been talking about all this time. I guess I should read what's up there too instead of think I remember what order I put them in. Torque is a cross product. It's not the only cross product we're going to be seeing, it's just the first one we've seen. So what does a cross product mean? You're multiplying the perpendicular parts of vectors. So if you use that in normal math, that just means multiplication. But if it's two vectors, it means a cross product. So you got to be a little flexible with your math symbols. So that cross product is multiplying perpendicular components of vectors, and it's always find the direction using the right-hand rule. Don't use the left hand for the right-hand rule. It's an easy mistake to make, especially if you're writing with your right hand and you're sitting here trying to figure things out. You actually put up your left hand and do it wrong because the left hand is a mirror image of the right hand. So remember the rule, if I have a basic, I can't write this upside down. If I have a basic equation, vector A cross vector B equals vector C, the direction is found by taking my index finger and putting the direction of which of those vectors? A. And then keeping my index finger in that direction, I orient my hand so my middle finger can point in the direction of which vector? B. B. And then how do I find the direction of vector C? Whichever way the thumb is pointing. So make sure you understand how that's used. It's likely you'll have a question that's not a torque question, but a cross product question to make sure you understand how the cross product works.
Say it one more time.
The right hand rule? Yeah. The index finger points in the direction of the first vector in the cross product, so the one before the X. The middle finger, you keep that index finger the same direction, rotate your hand so your middle finger can point in the direction of the second vector, the one that comes after the X. And your thumb points in the direction of the answer. And because of this specificity, A cross B is not equal to B cross A. They're opposite directions. Question?
Can you tell us how you point towards the radius for one and you point towards the direction of force for the other one?
You're moving your fingers wrong again.
Yeah.
Well, okay, so if we have a case of I have an object and there is a force acting here on the object, and I want to sum the torques about this location. Okay, so there I have everything specified. The first thing I have to do is I have to identify, well, my equation is torque vector is equal to R vector cross F vector, where R vector is the vector that goes from the point I'm summing the torques to where the force acts. So in this case, my R vector is like that. And my force vector already has a direction shown, but I didn't put a vector sign on it because, well, I thought I changed colors, but I knew I'd made a mistake. So now with that drawn, I take my right hand, I point my index finger in the direction of R. So my index finger has to point this way. Then keeping it pointing that way, I orient my hand so my middle finger can point in the direction of F. And my thumb points into the board, hence that would be a torque into the board. And then it depends on how you define your X, Y, and Z directions, if that's a positive or negative torque, actually. We usually define out of the board as the positive direction, into the board as the negative.
So your index finger points are away from the fulcrum point?
Yes, your index finger points away from the fulcrum to where the force acts. All right. So that was 1. 3, be able to apply the conditions of equilibrium to solve a problem and know the conditions for stable, unstable. Okay, we didn't talk about stable, unstable, and neutral equilibrium this year. So we're not going to have that. I will give you very briefly what it is. Stable equilibrium means that if I displace something from equilibrium, it will come back. So this here, it's an equilibrium, right? If I displace it by tipping it, tip it, it will come back. So that's stable. Neutral equilibrium is if I displace it, it finds a new equilibrium. Doesn't come back, doesn't go flying away, just finds a new equilibrium. So if I push this a little, it just found a new equilibrium. So for sliding, it was neutral. For tipping, it was stable. Unstable, I certainly will not demonstrate with a piece of glass. Unstable means that if you tip it, it won't come back. Imagine that I have this balanced. It's possible, right? That would be an equilibrium. But if I had this balanced and anything happened, like, I don't know, someone breathed in this room, God forbid, it would displace it from equilibrium and it would fall, go away from it. That's unstable equilibrium. And the basic rule of thumb is, if the center of mass is over the support, then you're going to be in stable equilibrium. So like with me standing here, my center of mass is somewhere around here. If you try to tip me left or right, my center of mass is going to have to rise as I tip. And so I come back. And as long as that center of mass is over my feet, I'm going to be stable. But if the center of mass moves outside of the feet, then it's unstable and I fall. So I'm stable for a small tip, unstable for a big tip. There's fun things we do in physics class. Things like get somebody who's not super flexible and have them stand with their back against the wall and then keeping their legs straight, reach down and touch their toes. A normal human can't do this. A very flexible person may be able to. But what happens when I lean forward to touch my toes, I have to lean forward, right? If I keep my legs straight. And so what's happening to my center mass? It's going forward. And if it goes out in front of my toes, down goes Tyson, right? Okay. A problem with equilibrium to make sure we have this down. So, of course, I got to go to the other app so I can do the problem. NFL rules. By the way, do you notice that probably all the teams we care about in this room won yesterday? No? Well, the NFL, they play football. They specify that a goalpost has to have 2 posts that are 18.5 feet apart and a crossbar that's 10 feet off the ground. The goalposts are supported by a single standard gooseneck. That's this thing right here. That places the post 2 yards in front of the single support. The single standard is buried 53 inches. These are all NFL specifications. What additional horizontal force must the bottom of the hole supply to counter a 95 kilogram fan standing on the crossbar at one of the posts? So I have a fan standing right here. Why do I have such a problem? Because when I was in graduate school, of course, almost every football game was on Sabbath, but there was one that was on Saturday night ESPN football. So I was there. We won the game, and afterwards the students rushed the field. Not just one fan, but 10 fans climb up on the goalpost. Goalposts come down. Students then took the goalpost, marched out of the stadium with the goalpost, went to a bar, left the goalpost outside the bar. And yeah, that's why I have this question. Responsibility? Yeah. So here's the question. If you have a student standing there, of course, student, that's college for NFL. How much additional force are you going to have to supply at the, and notice I was specific, at the bottom of the hole to counter that student? What kind of problem is this?
Equilibrium.
Okay? It's an equilibrium problem. Oh, look, yes, it says equilibrium problem. That won't be there on the test to tell you. So if it's an equilibrium problem, what rules do I have?
Sum of the torques is 0.
Okay, sum of the torques is 0, sum of the forces is 0. Notice these are vectors, so any direction I choose to sum them, I'm going to get 0. So, which rule should I probably start with? Torques, yeah. But what do I need to do before I do anything?
I need to draw your forces.
I need to draw a diagram and show the forces. So I'm going to show a side view. So the side view we have the fan is standing here. This distance is 2.0 yards. This distance here is 10 feet. And this distance here was, let's say, 53 inches. So there's a basic diagram looking at it from the side. And then if I indicate my forces, I asked about additional, so I'm not putting in anything about the weight of the goalpost. That's already incorporated into the way it was designed. So the force of gravity of the student is equal to mass of the student times g. And then I'm going to have some forces. I'm going to have a force that's pushing up, force bottom, I'll call it y using our standard. Actually, I better call it z. So there's my right-hand coordinate system, right-hand because x cross y equals z. So I have the force in the z direction on the base, and then because this person has a downward force, it would make the whole, in this picture, it would make it look like the whole situation is going to rotate this direction, right? And so I'm going to need a force here to counter that, which is going to have to point.
Yeah.
So I'm going to have force bottom in the, it's actually XY direction. It's a combination of the X and Y directions. And then there is another force, the force here, force of the ground, let's not use G, force of the earth in the XY direction. Now I've got this XY direction. I need a second picture so I can specify what's going on with the XY direction. So I'm going to shift from that picture to a top view picture. And of course, we've never done a problem that's three-dimensional, have we? So it's a little bit more fun. So looking at it from the top, we have, here's the goal post. There it goes down to the ground. And we have the person standing here. And so we have force of gravity for the student is equal to mass of the student times g down. And we have our forces. There's force bottom XY. And there's also going to be force of the earth XY there. So I have my forces marked. There's an upward force at the bottom. I guess I should have put that to force bottom Z there. And then I'll put some dimensions on here. 2.0 yards. And that's half of 18.5 feet, so 9.25 feet. Now, when you look at this, between the two pictures, oh, should I specify X and Y directions? Yes, I should. The X direction was like this. The Y direction was like that. And the Z direction is coming out. So I got these two pictures. We said already, how am I going to approach this? Now that I've drawn my picture, I'm going to start with summing the torques. And when you're summing the torques, you have to make a further decision, where do you sum them? You want to sum them about a location with an unknown force that you're not looking for. So the force I'm looking for, actually the problem tells you where to sum it. What is the additional horizontal force at the bottom of the hole? So I'm looking for this force. So what forces do I not know? Which one? Okay, I don't know the force of the earth. I also don't know, of course, the one I circled because I'm looking for that. And I don't know the Y or the Z component of it either. So I want to choose a location where I can sum the torques that's going to eliminate at least one of the unknown forces. Well, if you look at the picture as viewed in the side view, there's a location where both the vertical component of the bottom force and the earth force point. Where's the location where both of those forces point? Yeah, where it comes out of the earth. So if we sum the torques about that location, I always give it a location, so of course I'll just call it A. If we sum the torques about A, then we'll have the perpendicular distance for both force By and force E, xy, is equal to 0. And so that's going to make my life easier. Sum of the torques about A equals, and you might think, oh, he should do it about the x-axis, about the y-axis, about the z-axis. But I can shorten my work quite a bit by recognizing that all three of those forces are going to be making torques about a single axis through that point that goes like this. So I'm going to sum the torques about that axis, which I don't have a name for. But I'm going to sum the torques about that axis. And so I need R cross F. Write the equation here so we don't forget. Torque is equal to R cross F. Why is the equation I've written right now incorrect? Doesn't have the vector signs. It means something different without the vector signs. The magnitude of the torque is equal to R perpendicular times F, or RF times sine of the angle between R and F. If we look at the top view, we can see that the perpendicular distance between A and where the person stands is the hypotenuse of a right triangle. And so our perpendicular for this force is simply going to be 2 yards is 6 feet. So the square root is 6 feet squared plus 9.25 feet squared. So R for the student is square root of 6.0 feet quantity squared plus 9.25 feet quantity squared. And let's just get a number for that. On 6 squared plus 9.25 squared. And then square root that bad boy. So we have 11.026 feet is the perpendicular distance from where I'm summing the forces, or the torques, to where the forces to next. Yeah, that's a question.
Where is the 6 feet in the question? It's not in the diagram.
Yes, it is. 2 yards is 6 feet. So it was from that triangle. Sarah, you had a question?
On the test, since
Yeah.
we've never done three-dimensional problems before, are we gonna have a three-dimensional
No.
problem on the test?
No, the goal is to give you something that's a little more so you back down for the test, rather than to give you something that's a little less so you step up for the test.
This is an absolute nightmare.
Yeah, I was like, oh, I was
You should understand what's happening. You should understand what's happening because we're simply applying a rule. The application has more difficulty because we have to think about the directions more carefully. Right, which is how I got this 11.026 feet. So now my torques, I have my perpendicular distance of 11.026 feet times the mass of the student times G. And I have to decide, since I'm not using a standard axis, is that going to be a positive or negative torque? I will take the point of view that I am standing in the bottom left. And so my R is pointing like that. The force is pointing into the picture. The torque is pointing this direction. And I'll go ahead and call that a negative torque. It kind of comes up to how you want to define what direction is positive and negative. Then I have the counter torque. And the counter torque to that, I can most easily pick up from looking at the side view. Because looking at the side view, we see that from point A to the perpendicular distance to force BXY is that 53 inches. Times the force base XY, which is what we're looking for. Wow, that's a lot of work, right? What's the sum of the torques going to equal? 0 because it's equilibrium. We can't forget what we're doing halfway through. We've gone in a lot. We start to get muddled up. We can't forget where we're headed. So I'm looking for the force BXY. So I will add this to both sides of my equation. I have 53.0 inches times force BXY equals 11.026 feet times the mass of the student, which was 95.0 kilograms, times G, 9.80 meters per second squared. Well, to get FBXY, I just have to divide everything by 53.0 inches. Now, if you pop this in your calculator, you're going to have some weird units. We have to do some unit conversion.
Can we just change from inches to feet in order
Yeah.
to cancel out the feet?
If we change from inches to feet, we're going to get the force in newtons. So I have feet on top, inches on bottom. So let's multiply it by inches on top and feet on bottom. 12 inches to 1 foot. I don't know why I'm inconsistent there. 12 inches to 1 foot. And so now if you multiply everything through, you will have the additional force necessary to counter that person. Using appropriate significant digits, the additional base force is 2,320 newtons. So in terms of how in-depth the problem is, the problem itself wasn't super in-depth. What made it difficult? The spatial relationships. And you're not going to have a three-dimensional problem on the test. All I cared to know is this problem will help me prepare, but it won't be on the test. Okay, any questions about the problem? Would you have been able to identify which type of problem it was if it didn't say equilibrium problem?
Yeah.
Yes. Would you have written that down if it was one of the final three? Yes, you would have written it down because then I can give you credit for identifying that. Now, of course, if it's not an equilibrium problem, you don't get credit for writing down the wrong thing. Just to make sure it's clear. Once you specified it's an equilibrium problem, then you knew I have some of the forces zero, some of the torques is zero. I'm probably going to start with some of the torques. We drew a picture, we identified our unknown forces. From that point, we realized I can solve this in one step if I choose the right location to sum the torques. And then we did that one step. Okay, that was chapter 9. Chapter 10. Rotational dynamics. So rotational dynamics, now we're dealing with accelerations or angular acceleration. So we still have essentially Newton's second law. Sum of the forces is mass times acceleration. But we have the rotational form, sum of the torques is equal to moment of inertia times angular acceleration. So we have two equations, one for rotational equivalent of Newton's second law, one for the linear. And we're going to have to use both. Oh, I forgot. Yeah, of course, I have different order up here. You see, I just have there. The second one is what I talked about again. Make sure you know what the rotational quantities are. Make sure you know what angular momentum is. In a practical sense, that's not an equation. What is angular momentum? What is linear momentum?
Momentum in a straight line.
Okay, it's momentum in a straight line, but in a practical sense, what does that mean?
How much energy has to go in and stop?
Okay, not energy, but that's the idea. The momentum is a measurement telling you essentially how easy or hard it is to change its motion. The higher the momentum, the harder it's going to be to stop. And it's telling you about its motion in a straight line. Rotational or angular momentum is telling you how hard it's going to be to stop it from rotating. So the higher the rotational angular momentum, the harder it's going to be to stop it from rotating. What do we call the rotational equivalent to a force that's going to change rotation? Torque. So that's why there's the innate relationship between torque and angular momentum. And so you remember the experiment we did with Andy. I hope everything's okay in her recovery. She expected to be here by now. But you remember her spinning, and when she brought those masses in, she had no external torques acting on herself, which means that her angular momentum, her rotational momentum, should have stayed constant. When she brought those masses in, she sped up. How did those two work together? How is that possible? How could her angular momentum stay the same when she rotated faster? I swear Sarah has an idea, but I can't pick up what she's saying.
Did you decrease our radius?
She decreased the radius, which decreased the moment of inertia, which is the rotational equivalent to mass. You can't change your mass easily, sure. You can cut off an arm and that changes your mass, but we're not doing that. So basically, we consider your mass fixed. But with rotation, you just change the orientation, the positions of things, and you change the rotational equivalent to mass, the moment of inertia. So she lowered the moment of inertia. If she's going to maintain a constant angular momentum, she had to spin faster. And a torque would have been necessary to actually change the angular momentum. Okay, let's move on. Be able to solve rotational dynamics problems using the work energy method or the forces and torques. Now, if you looked at the problem I gave you, yo-yo, I had two pieces. One, if you're going to do it without calculus, you can only do each one way. If you're going to do it without calculus, to find the final speed, you need to use the work energy relation. If you want to find the final acceleration, you have to use the Newton's second law with rotational equivalent. So I ran down and did both types of problems there, just so you could have some practice. Now, don't forget conceptual things like we have the relationship between torque and angular momentum is that the net torque is equal to delta L over delta T. What does L stand for? L stands for angular momentum. So change in angular momentum over change in time is equal to that funny, almost like a T thing is a tau for torque. So we had things like the bicycle problem. You lean on the bicycle and you create a torque. But when you create a torque, that means that your angular momentum is going to change in response to that torque. And so that's why you have the bicycle tire. When you lean right, you create a forward torque, so the angular momentum that was pointing to your left shifts forward, making the front tire rotate to the right, making you turn right. Or if you lean left, what direction is the torque you're creating?
Forward or backward.
Backward. And so then your angular momentum of that front tire has to shift backward, and you turn left. So anyone here watch like the X Games, that kind of stuff? A couple. You see people do crazy tricks on motorcycles, jumping them, and you may or may not notice that they do things like brake and accelerate when they're in the air to change the attitude of the bike, to make it so it will change the orientation, because they're playing with that equation right there. The net torque is equal to delta L over delta T. They're in the air. There's no external forces that can put a net torque on them. But if they put an internal torque on the tire and make it spin faster to conserve angular momentum, the rest of the bike has to do something in response. This also is actually, true. You guys have probably heard cats. You drop a cat, what happens? Land on its feet. I actually heard this when I was a child. We had a cat. We very originally named this cat Calico. And so little 7-year-old, 6-year-old, whatever I was, junior scientist Richard took Calico and held Calico one step off the ground by her feet upside down and let go. She landed on her back. But I was not done. I went to the second step and did it again. You have a point. I went for every step up to about 18 steps, and after about the 4th step, she landed on her feet every time.
18 steps.
I probably was. I'm not proud of that aspect. But that's what science is. You're doing an experiment to test an idea. No, it's not torturing cats. I did. I feel bad about that. Okay.
Torturing a cat.
How? Well, no, I'm not telling you to do that. How is it possible for my beloved cat to land on its feet anytime we were above about 4 steps? But how does it reorient? It started stationary with its back down, no net torques. How does it make itself rotate?
Internal forces.
Okay, it's internal forces. What they do is essentially you put your paws out and you rotate, then you put them here and you let it rotate for a little bit, and then you bring them out and you rotate back. And you can change the orientation. And the cats are crazy good at that. They're taking advantage of this equation. Just like figure skaters do, just like divers do, just like snow ski jumpers do. That's what I love to watch. Okay, my cat was a very nice cat. Fluid statics.
Was past tense, but died.
Well, yes, because a tomcat came and tried to eat her kittens, and she fought him off as much as she could. But we came home and only able to save like 2. And she pretty much lost touch with reality. We just went around going, and so yeah, she's dead now.
Oh.
She would have also died from old age by now, but I'm sorry that you asked and I answered. So, remember we talked about The differences is solids, liquids, and gases. I talked about what you guys learned in grade school about these, but apparently grade school science isn't the same everywhere, and you didn't learn these things the same way I did. But solids, each atom has a fixed position in a solid. The atoms aren't moving past each other, they're fixed positions. So we have atoms. For a solid, they're fixed. What about for a liquid?
They're not fixed, but, well,
They're stuck together, but can move around. So they can move past each other. Okay, that was a long one for liquid. What about gas?
neither stuck together and they can move around.
They're free. The atoms can go wherever they like in a gas. So the fundamental difference between solid, liquid, and gas is the motion of the atoms. But those motions give us then some outcomes. So when we talk about the shape, if it's a solid, because the atoms are stuck in one position, the shape is fixed. It can't change shape because that would require the atoms to move about. Whereas the liquid, it can change. It changes to whatever its environment. So for instance, if I take this and I put water in, the water will take on the shape of this. And if I tilt it, the shape of the water changes as I tilt it. If I had a solid, i.e. this bar, that solid, no matter how I shift or move it about, stays the same shape. Now with a gas, the molecules and atoms, I said atoms here, but it could be molecules, they're free. So what does that mean about their shape?
They fit the environment.
They also fit the environment. And they will completely fill your environment. So in this classroom, the molecules completely fill the classroom. The last one that we talk about is the volume. And so a solid with the atoms fixed, its volume is fixed. A liquid with the atoms free to move past each other but not able to get away from each other, that's also fixed. The gas, on the other hand, with them free to move wherever they like, that is Bill's container. So we have those last two columns, the shape and the volume, are based on the first column. And keep in mind things like fixed shape and fixed volume, those are mostly terms. They're not absolutely. If I take, I gave you a problem, how far would you have to take a balloon filled with nitrogen gas down in the water until it sinks? The answer comes out to be almost 9 kilometers deep. If you were to get more careful, you would have to start admitting it's probably not an ideal gas by the time you get to that density. And so it fails before you get there. But the reason that can occur is because the gas is squashed. But if I were to take something solid, like let's say a brick of iron, and take it down to that same depth, that brick of iron would also decrease in volume a small amount. The difference is it would be a small amount, whereas the gas is a large amount. So we say nearly incompressible when we want to be accurate. And likewise, nearly undeformable. If I have a solid, if I take this and I push on it, I can take the solid and I can flex it, right? It wasn't perfectly fixed. So you have to understand that with these. Don't take it too far It's nearly fixed there. Okay, identify which of these primary states of matter are considered a fluid and why. Which ones are fluids? Liquid and gas. Why? What makes them fluids?
Because they change the environment.
They can flow. Anything that can flow is a fluid. And we talked about, don't get confused, don't start saying, oh, because glass can flow over the course of millions of years, it's a liquid. That's kind of nonsense that people say. Okay, understand hydrostatic pressure. Hydrostatic pressure is like stress, that is a force creating area, but it's the same in all directions. So the air pressure that's pushing on my hand pushes down on the top, pushes up on the bottom, and the pressure doesn't change much in that. Height difference, so it's equal. Pressure does change a little bit with depth though, right? We had change in pressure was equal to density, GH. So that means air pressure is technically higher at the bottom of my feet than it is at the top of my head. Well, what's the result if I have a higher air pressure at the bottom of my feet than I have at the top of my head? I have a little bit of a buoyant force. It's not enough to make me levitate. But I have a little bit of a buoyant force lifting me up. Now, what would happen if I wore shoes that didn't allow air to go underneath them?
You'd be stuck there, wouldn't you?
I would be stuck because I would have the downward force due to air pressure that is, maybe 1,000 pounds. I would have to lift with to get my foot off the ground. Well, if they actually seal, we would call them suction cups, yes. But oftentimes we think, oh yeah, so my foot's on the ground and pushes all the air out. No, because if it did that, then I wouldn't be able to lift it back up.
Are the shoe like that?
Hmm?
Did you make a shoe like that?
Well, if you watch spy movies, they apparently have. It's only spy movies where they actually run up the side of a building. It's not real things, I don't think. Right? Because you would have to.
But if you could control it, you could though, right?
If you could, yeah. But think about the logistics of controlling it. So you put it on, it attaches when you want it, and then it detaches when you want it. Okay, Pascal's principle and Archimedes' principle. Those were the payoff problems from this section. We had Pascal's principle that says the technical description of Pascal's principle is if I can increase the pressure at one point in a constrained fluid, it increases everywhere by the same amount. But where I usually take it from that is, if it's constrained, the pressure at any elevation is going to be the same. As you go down, it's going to get bigger. Higher, it goes lower because that change of pressure is rho GH. And so that's like what we use for hydraulic systems. And make sure you can explain what surface tension is and how it does things like creates a meniscus or allows water striders to walk on water. You're not going to do a calculational problem with surface tension, but you need to be able to explain, cohesion, adhesion. It's the cohesion between molecules. The adhesion makes a meniscus. Make sure you have that down. You see more crossouts from chapter 12. We didn't talk about laminar turbulent flow this year. I should mention turbulent flow, the water goes tumbling and it makes cavitations. It makes little vacuum bubbles. Vacuum, what does the word vacuum mean?
Empty space.
Empty space, zero pressure. If there's molecules in there, it's not empty space and pressure isn't zero. So turbulent flow, you can hear when water is going through a pipe if it's turbulent flow because you actually hear the water tumbling in the pipe. Laminar flow, laminar means in layers. Laminar flow is smooth flow. And so if you have smooth laminar flow, you don't hear that going through the pipes. Make sure you understand the flow rate calculation. And if you have continuous flow rate, and you go to a region with a bigger cross-sectional area, what's going to happen to the speed? Decreases, slows down when you go to a bigger area. And if it slows down, what happens to the pressure? It increases, right. Because of Bernoulli's equation. How do we come up with Bernoulli's equation? It's using the work energy relation. It's derived using the work energy relation. And I had a problem here, which is very similar to a home problem, but we are out of time. Once again, I will be out of my office this afternoon because of my wife's medical procedure, but email me if you have questions. I apologize for not being in my office. Have a great day. I'll see you all tomorrow.